All right, so in this example, let's say we have two X versus Y graphs. We're just dealing with one single wave. Usually we would have a position graph and a time graph, but here we have just two position graphs and no time graph. So this is showing what the wave looks like. This is a snapshot of the shape of the wave at the instant time equals 6 seconds. And this is another snapshot of what the wave looks like at the instant time equals 10 seconds. So the entire shape of the wave at two different times as it moves. And this wave, maybe it's moving to the right or maybe it's moving to the left, could be either way, we don't know yet. The thing is, this alone, these two graphs, is actually not enough information to know if it's moving to the right or to the left, because this is just showing positions. Motion is about position and time. So we're gonna need to know some information about time. One way to do this is if we already know the speed. Like let's say we already are given the speed of the wave. Maybe we know what type of wave through what medium, and we already know that the speed is, let's say we are given that the speed is 2 meters per second. Work. Yeah. So if we know that the speed is 2 meters per second, that should be enough information to figure out everything else about the wave. And what properties of this wave could we measure from this graph?
The amplitude?
Yeah, we can measure the amplitude. Well, I didn't actually show the y values, but let me put in some.
Sorry. And like the period and frequency.
Let's say it goes up to 5 and down to -5. So that's our amplitude.
Measure the period, right?
Sorry, what was that?
Can't measure the period.
Yeah, this graph doesn't directly show the period. What information would you need to know to find the period directly?
Like the amount of time?
Right. Period is the amount of time for one full cycle. So if we had a T versus Y graph, we could find the period or frequency.
Couldn't we find it from the frequency?
Sorry, what was that?
Could we find it from the frequency? Because it's inversely related?
Yeah. Well, if we knew the period or the frequency, we could immediately find the other one. Period and frequency are basically the same information, just written in inverse ways. But period and frequency are just inverses of each other. But yeah, we can find wavelength, because this is wavelength is the distance from one full cycle to the next, from crest to crest or from trough to trough. And since these are graphs showing distance on the x-axis, then we can measure the wavelength. So that's going to be straightforward enough just by measuring from crest to crest or trough to trough. For example, looks like we've got a crest at x equals 4, and the next crest is x equals 10. So how far is it from crest to crest? Yeah, that looks like 6 meters. Those crests are 6 meters apart from each other. We could even measure, for instance, from trough to trough. Looks like this is from 3 to 9. 3 to 9 is also 6 meters. So either way you measure it, this graph has wavelength 6 meters. And of course, it should be the same on both graphs. The only difference between these graphs should be a shift one way or the other. They should be exact same shape, just shifted on the coordinate system. So we get the wavelength we can measure from the graph. Wavelength is 6 meters. Amplitude looks like 5 meters since it's going from 0 up to 5 and from 0 down to -5. Which also means we've got no vertical shift. It's centered around 0. And I think that's all we can measure directly from the graph. Everything else we're going to have to calculate. For example, period and frequency have been mentioned. How can we find the period and or the frequency from the information we now have? How is that related?
Speed is equal to frequency times the wavelength, so we can just divide the speed by the wavelength to find frequency.
Yeah, that should work. Speed is frequency times wavelength. So frequency is speed divided by wavelength. we're given the speed, we measured the wavelength. So frequency is speed divided by wavelength. 2/6 reduces to 1/3. And meters cancel out, so we just get 1/seconds, which we should interpret as cycles per second or hertz. So the frequency is 1/3 hertz, 1/3 of a cycle every second. And likewise, the period would be what?
3.
Right, 3 seconds per cycle. So the 1/3 of a cycle happens every second, 1/3 of an oscillation, which means it takes 3 seconds to complete one full cycle. 3 seconds per cycle. Any questions on that so far? So with this information so far, we should be able to write out most of the wave equation, although we're going to be missing a couple of things. We can certainly say that y equals our usual amplitude times sine of 2 pi t over period plus or minus 2 pi x over wavelength plus phase shift. And we know there's no plus y naught. It's not shifted vertically at all, so we don't need plus anything else outside the function. By the way, another way you can write this that's sometimes more useful, we usually write this as 2 pi times time divided by period. But dividing by period is the same as multiplying by what?
Frequency?
Yeah, which means divided by period could be rewritten as times frequency. We could write this entire first term as just 2 pi f times time. And this is sometimes an easier way of writing that out, especially if we're looking at differences. Later on, we're going to be seeing situations where you're looking at something happening, or 2 waves happening at the same time. If they're occurring at the same time, then time is a constant and can be factored out. And for delta frequency, it's often easier to subtract frequency 2 minus frequency 1 rather than 1 over period 2 minus 1 over period 1. So it's often easier to write this as 2 pi times frequency times time instead of 2 pi divided by period times time. Same thing, just a more useful way of writing it. And filling in the values we know the amplitude is 5. We know the frequency is 1/3. And we know the wavelength is 6. And what do we still need to figure out? All right, so we know the frequency, we know the wavelength. All we need to figure out now is direction of travel for the plus or minus, and somehow find the phase shift as well. Any questions on that so far? Okay, so if we have, if we need to find the phase shift is generally going to be the last one we need to find. But the, yeah, let me type that up. That's y equals 5 sine 2 pi over 3 t plus or minus 2 pi over 6 x plus phi. That's it. Yeah. So phase shift is usually going to be the last thing we find by plugging in everything else. The plus or minus we can find based on direction of travel. And for direction of travel, we can't find a point in common like we were earlier, because there isn't really a point in common. Point in common means a point on both graphs that has the same coordinates. But this entire graph is at time 6 seconds. We can't find 6 seconds on this graph because this entire graph is time equals 10 seconds. So there is no point in common. What we can do instead is look for, let's say, a crest on one graph, and as it moves, look for the same crest on the other graph. And to do that, Like we want to know, is this, maybe this crest here, we want to know, is this crest moving to the left and becoming this crest or this crest? Or is this crest moving to the right and becoming maybe this crest or another crest further on down the line? We want to figure out which crest on this graph is really the same as, let's say, this crest on this graph. So to do that, we need to find, again, a way of comparing position and time. And what one quantity brings together position and time?
Speed.
Yeah, the speed. And this is really why we need to know the speed. If we didn't know the speed, we wouldn't really have a way of telling which crest on this graph corresponds to which crest on this graph. We might be able to make an educated guess. We could just say, assume that this crest is the same as this crest and work from there. But if we know the speed, we can tell for sure. And we can do that by going back to the definition of speed, the idea that speed is distance over time. We know the speed. Do we have a distance or an amount of time associated with these graphs?
We have time.
Yeah, we know what times these occur. We know this entire graph is a snapshot at the instant 6 seconds. This entire graph is a snapshot at the instant 10 seconds. How much time passes between those?
4 seconds.
Right. There's a 4-second difference between these. This is like taking 2 photographs of the wave as it passes by 4 seconds apart. So that's delta t, the difference between these instants in time. And if we know speed and delta t, we can figure out what delta x is, figure out how far the wave travels during those intervening 4 seconds. And how would you solve for delta x here?
Multiply both sides by 6.
Multiply both sides by that amount of time, which is going to be 4 seconds. So multiply by 4 seconds, 2 times 4 would be 8 meters. So delta x must be 8 meters. In other words, during those 4 seconds, the 4 seconds that pass from this photograph to this photograph, during those 4 seconds, the wave travels 8 meters. So we should be looking for a crest on one graph and a crest on the other graph that are exactly 8 meters apart from each other. Any questions on that so far?
Why are we looking at the crest specifically?
It doesn't have to be a crest. You could use any point on the graph, but it's easiest to identify a point on the graph and the same point on the other graph if you're using a unique point like a crest or a trough.
Okay.
So what you want to do is pick a crest, any crest or trough, usually from near the center of one of the graphs. For example, let's say this trough here. We've got a trough at x equals, looks like 7. And we know that 4 seconds later, that crest or that trough has to have moved exactly 8 meters. But we don't know which direction. Maybe it's at 7 and it moves 8 meters to the left. Maybe it's at 7 and moves 8 meters to the right. So we should check both possibilities. If it's at 7 and moves 8 meters to the right, where would it end up? Yeah, 7 plus 8 meters to the right would be 15. So maybe it moves 8 meters to the right and ends up at 15. Or maybe it moves 8 meters to the left and ends up where? Yeah, start at 7, move 8 meters to the left, you end up at -1. So if you've got a trough that starts off at x equals 7 at some instant in time, it might be moving 8 meters in either direction during those 4 seconds. Maybe it moves 8 meters to the left and ends at 15. Maybe it moves 8 to the left and ends up at -1. So we should check both of those points on the other graph, because the other graph is what represents 4 seconds later. So we check -1 on this graph, And that's a little past the graph, but we can extend the curve a little bit. Does it look like we expect a trough at -1? Doesn't look like it. It looks like it's maybe, at best, maybe passing through equilibrium. But if we look at positive 15, we have a trough at positive 15. Yeah, this trough at 15 is the same as this trough at 7. So this trough right here is actually the same as this trough right here. Exact same trough, just different positions because we're looking at it at different times. It has moved from one place to the other. Any questions on identifying that same trough?
So like, it's like, sorry, I don't know what I'm trying to say. It's just like, with this type of problem, like, so we need to know, like the information we need to know to solve, we need to be aware of like the period, right? Like that's really important to solve this type of problem because,
yes.
Okay. Oh wait, sorry, I got confused because I thought the period was 4 seconds, but we identified that the period was only 3 seconds. Okay, thank you.
Yeah, the 4 seconds was from looking at or comparing these two.
Yeah. Okay, but then we still needed the period, or was the period not necessary to solve for this, for the direction of the wave?
The period is, of course, necessary for figuring out, for filling in the equation itself.
Okay, okay, thank you.
Note that we got that information from the given velocity. This also could go the other way. Maybe we don't know the velocity, but it told us the frequency or the period. You could use the frequency or period to calculate the velocity as well, using v equals wavelength times frequency. But as long as you know something about the speed or the time, then that should work.
I have kind of a side question.
Mm-hmm.
If say we were given like 2 y versus t graphs instead of 2 y versus x graphs,
Mm-hmm.
would you solve it like the same way, except for like when you do v equals delta x over delta t, you would like plug in delta x and then solve for delta t and like test it?
Yeah.
Okay.
Yeah, exact same procedure, just different information that is known already. If these had been t versus y graphs, each one would have an x value. So you compare the two x values, subtract to find delta x, and then solve for delta t. So then instead of looking at a crest and looking to the left and to the right, you'd be looking at a crest or a trough on one graph and look for a certain amount of time into the past or into the future on the other graph, which still looks like left and right on the graph, but it means into the past and into the future. But you're still trying to identify the same crest on both graphs or the same trough on both graphs, just at a different time because it's at a different position. And at that point, once you've identified the same crest on both graphs or the same trough on both graphs, I find it's helpful to draw out a picture of the shape of the wave. Regardless of whether you've got x versus y graphs or x versus t graphs, once you've got the coordinates, we know, for instance, that this trough hits the 7-meter mark at some instant in time. And it also hits the 15-meter mark at some instant in time. So if this is an x-axis, if this is just a map of the surface that the wave is traveling through, we know that a crest or a trough, a certain trough hits the 7-meter mark at time 6 seconds. And that exact same trough hits the 15-meter mark at time 10 seconds. Of those, which one happens first?
The 7-meter?
Yeah, 6 seconds, the wave, this trough hits the 7-meter mark. And then 4 seconds later, the same trough hits the 15-meter mark. So in terms of passage of time, the wave is traveling from 7 meters towards 15 meters. That's the direction of travel. And the nice thing about a diagram like this is it works regardless of whether you're dealing with two x graphs or two time graphs. If this had been two time graphs, once you've identified the same trough or same crest on both, you can still draw out an x-axis and say it hit this location at this time and this other location at this other time. Ask yourself which one of those times happens first, and that'll suggest which direction the wave is traveling, from the earlier time location to the later time location. Any questions on that so far? Left moving wave would be maybe if we had, like if this had been time equals 6 seconds and this had been time equals 10 seconds. If it was the exact same setup, but if the trough had hit 15 meters at an earlier time and hit 7 meters at a later time. Yeah, exactly. You've got to combine time and position, because you can't really have motion with just position or just time. Motion involves position and time. Any other questions on that so far? And if it's moving to the right, what does that suggest about this plus or minus sign?
Minus.
Yeah, that will specifically be a minus because the wave is moving in the positive x direction. That means the only thing left is finding the phase shift, the value of phi. And how do we find that?
We can just like pick a point, like a trough or a crest.
We can find any point from either one of these graphs. And yeah, a crest or a trough would work best because those are unambiguous. There's only one crest in each cycle, only one trough in each cycle. So let's try that. If we just take any crest or trough, let's say maybe this one. We know there's a crest at x equals 12, t equals 10, because this whole graph is t equals 10. So we can substitute 12 for x, 10 for t in the total phase. So if I just write out the total phase, so 2 pi over 3 times time, which is 10, minus 2 pi over 6 times x, which is 12, plus this unknown phase constant. What total phase should that add up to if we're talking about a crest?
Pi over 2.
Yeah, we can set that equal to pi over 2 because we're at a maximum, and sine of pi over 2 is the largest it can be. So simplifying this, we've got 20 pi over 3. Actually, since we've got 6, 3, and 2, I think it's probably going to work best to put everything in terms of sixths to get a common denominator. So 20 pi over 3 is the same as 40 pi over 6. Just multiplying numerator and denominator by 2. And this one, instead of reducing it, I'm just going to leave it in sixths. 2 times 12 would be 24 pi over 6 plus phi. And likewise, let's put this in sixths also. Times 3, so we get 3 pi over 6. 40 minus 24 would be 16. And then we can just subtract 16 pi over 6 from both sides. So we get 3 minus 16 would be negative 13 pi over 6. So this would be one way of writing out the phase shift, negative 13 pi over 6. Any questions on that process so far?
My TA said that we have to make it within like negative 2 pi and 2 pi.
Yeah, in fact, I would even make that a little more specific. I would say from 0 to 2 pi, because this is a correct value. This is mathematically just fine. This works as a value of phase shift. You graph this equation using negative 13 pi over 6, you will get these graphs. But it's usually better to have a phase shift value between 0 and 2 pi just to make it easier to work, numbers easier to work with. And also for consistency. It's nice if we can have everybody who's writing an equation for these graphs get the same result, rather than having to check, well, those are two different phase shifts. Are they equivalent or are they really different? So we can modify this phase shift. What can you always add to an angle that doesn't really change the angle?
2 pi.
Yeah, you can always add or subtract 2 pi, or even any whole number multiple of 2 pi. Because 2 pi, if you've got some angle and you add 2 pi, that's 1 full revolution. Gets you back to the exact same location. Or if you add 4 pi, that's 2 full revolutions, but it gets you back to the same location. So we can just add 2 pi to this. If it's negative, just keep adding 2 pi, adding 2 pi, adding 2 pi, or add any even multiple of pi until it becomes just barely positive. Would 2 pi be enough to make this positive? Not quite, because 2 pi is how many sixths? That's just going to be, yeah, 12 pi over 6. That doesn't quite make this positive. We could just leave it as that. We could add 12 pi over 6 and get negative pi over 6. So you could say the phase shift is negative pi over 6. But it's better if we can make it a small positive number. So let's add another 12 pi over 6. In other words, 24 pi over 6. And I think that's going to end up as 11 pi over 6. That is positive, and it's not bigger than 2 pi. So this fits the recommendation of a phase shift between 0 and 2 pi, the first full cycle. So that's what we're going to use as the phase shift. Any questions on that equation?
May I ask a question about adding 2 pi and subtracting 2 pi?
Yeah, go ahead.
So if you, just to clarify, if you add 2 pi to your binod, you'll still get the same result to your total phase. Like the total, if you add 2 pi to your total phase, it'll be the same, right?
Well,
Like
I mean, it does change the total phase, but it doesn't change what's actually happening. Like for instance, if the total phase is pi over 2, you're at a crest. If you add 2 pi to that, you get 5 pi over 2, but that's still a crest. Sine of 5 pi over 2 and sine of pi over 2 give you the same result.
Thank you, I appreciate it.
So we've used these two graphs and the velocity to get an equation for the wave. And I think someone earlier was asking, how would you draw another graph? If you had, like here we have two x graphs, how could you use this information to also draw a time graph? So let's try that as well. Now that we've got all this information and the equation, which brings all that information together, let's see if we can use that to draw a time graph also. Draw a t versus y graph. And of course, this needs to be at some specific x value. Let's say at x equals, let's say x equals 4. I think that'll work. So t versus y graph. And we know the period was 3 seconds. Let's just graph this for, let's say, 3 periods from 0 to 9 seconds. We know it's going to go as high as 5 and as low as -5. We know the period is 3 seconds from earlier. So it's going to be 3 seconds for each full cycle. The problem is that gives us most of the information about the shape, but it doesn't really tell us where to begin. We're going to need some sort of starting point to anchor everything on. Is there anything we know about what's going on? Is there any point, any time we can tell whether it's going to be a crest versus a trough?
We know that at t equals 6 at time, or 6 seconds, it's going to be at a crest, and that at 10 seconds, it's going to be somewhere close to a trough, but not really a trough.
Because this whole graph is for x equals 4. We've got information about x equals 4 from both of these graphs. So we know for sure we've got a crest at x equals 4 at time equals 6. Yes, the x equals 4 would have to be given. Or maybe you just choose a point or choose an x value. Because yeah, we're trying to draw a t versus y graph. So the challenge here is you've already got two x versus y graphs. We want to draw a new t versus y graph depicting the exact same wave phenomenon. We're just drawing the different graph of it. So maybe we want to know, like, let's say we put a marker at x equals 4. It's going to be bobbing up and down as the wave passes. We're trying to draw a graph showing the history of that marker as it bobs up and down. So we know that at x equals 4 and time equals 6, there's a crest. So time equals 6, we're going to mark a crest. Time equals 6, crest. Crest at time equals 6, x equals 4. And that actually should be enough information to build everything else from. We could put this point on the graph also just to get an extra piece of information. We know at time equals 10, it's going to be part way down to a trough. So t equals 10, part way down, just as a reminder. But the crest is really, crest or a trough is really the important part, if you can get one. And now we should be able to draw out the rest, because we know, for instance, that the period is 3 seconds. If you're at a crest and you go forward in time exactly 1 period, what are you at? Yeah, exactly. Every period, 3 seconds later will be a crest. So 9 is a crest, 12 would be a crest, or if we go backward in time, backwards 3 seconds, 3 would also be a crest. Backwards in time, 3 seconds, 0 would be a crest. And then with all that, we can fill in the in-between values. What do you expect exactly halfway between two adjacent crests? Yeah, we're going to get a trough, a low point. So for example, exactly halfway between 0 and 3, 1.5 is going to be a trough. Halfway between 3 and 6, 4.5 is going to be a trough. Halfway between 6 and 9, 7.5 is going to be a trough. And likewise, halfway between 9 and 12, 10.5 would be a trough. And then halfway between adjacent crest and trough is going to be passing through equilibrium. So we could fill in the equilibrium points at 3/4, 2 1/4, 3 3/4, 4 1/4, a third, 3 1/3. Is that a third? Yeah, the in-between points. I guess that is quarters. 6 3/4, 7 1/4, 9 3/4. Yeah. And that should be enough information that from now on, it's just a game of connect the dots. Smooth curve connecting these points. Make sure it's flat at every crest and trough, because at a crest or a trough, at a max or a min, the derivative is 0 at that instant. So there's our graph of time versus y at that specific location.
Sorry, can you explain how you got the equilibrium points again?
Yeah, it's going to be passing through equilibrium halfway between adjacent crest and trough. So if you know where there's a crest and where there's a trough, if you know that at this instant, there's a crest, and at this later instant, there's a trough, or vice versa, exactly halfway between those in terms of the t-axis or x-axis, it'll be passing through equilibrium. So crest, trough, and you might find it useful to just draw a very short horizontal line at each crest and trough as a reminder that it's going to be flat at those instants. It's a good way to get a very accurate looking sine wave. Got to be flat at each crest and trough and steepest as it's passing through equilibrium, whether it's on the way up or on the way down. Any other questions on that? All right, then that's it for now. We will take a look at the Doppler effect next time, or any other examples you'd like to try out. See you then. You're welcome.